So what are the requirements of a catalyst actually? So there are several requirements we can talk about. High activity, that is the most important one. Good heat transfer. I mean, you want to make sure that it is also getting heated and cooled at the same time. Low pressure drop. You don't want too much pressure drop. Low carbon formation and high physical strength. These are all very important things. One of the things which happens in the carbon is in the catalyst is anytime you have a shutdown of your steam reformer, the expansion and contraction of the catalyst takes place. So every time you do that, you will have some breakage of the catalyst. And generally, the reformer pressure drop will continue to increase every time, maybe by about 5%. So those are some of the things. And the conditions are so extreme, you want high physical strength, you want high activity, all these type of things is what you need. So let's talk about what catalyst is used in reforming process, steam methane reforming process. Well, almost all of you got it right. It's a nickel catalyst. Yes, even though we can use platinum, rhodium, some of these catalysts, but nickel is the most common catalyst which is used in the steam methane reforming. So nickel-based catalyst, and the base is typically alumina or zirconium dioxide or magnesium dioxide. They are used as catalyst supports. So that's the shape of catalyst you can see over here. This is very different from what I used to see 40 years ago, more than 40 years ago. Though that time the catalyst used to be Rashig rings, but now you can see they have much different design to maximize the surface. They have got holes, so basically the number of active sites is much more, that catalyst is much higher active. So reformer pressure drop again is an important parameter, depends on the number of tubes, tube diameter, and catalyst types. Those are the three parameters. So let's find out from all of you what is the pressure drop across that catalyst tube in your SMR furnace. So the typical pressure drop in the industry, what we use is anywhere between 30 to 40 psi. I see everywhere, but 30 to 40 psi or 2 kgs, 2 to 2.5 kgs per centimeter square is typically the pressure drop used in most of the reformer designs. You don't want too high a pressure drop, and you also don't want a very low pressure drop. One of the important things about catalyst is to making sure that catalyst does not lose its activity. And there are several reasons which can happen. Some of them is sintering. Sintering is high temperature exposure. A lot of times because of high temperature, the catalyst gets sintered. Others are sulfur we talked about, carbon or coke depositions, and thermal aging. And all these things leads to uh, decrease in the activity of the catalyst, and you are forced to change the catalyst. So let's find out how often do you change your catalyst in your SMR furnace. All right, so most of the people are changing 2 to 4 years. There are some who has never changed it, but I think 3 to 4 years or maximum 5 years is the life of the catalyst. That's what I've seen in the experience. Although some people have changed it even after 2 years also, or less than 2 years. That could be because of mal-operation or power failure or some maybe water going into the catalyst, those type of things. So the SMR furnace design factors, there are 4 major important factors. We're talking about steam to carbon ratio, operating pressure, of outlet temperature, and radiant heat flux. These are the 4 important parameters that you want to design. So inlet outlet temperatures. The inlet temperature is typically around 1000 to 1050 degrees F. We want to maximize the preheating in the convection section, and so that the catalyst size or the reformer size is minimized. Outlet temperature is typically kept around 1550 to 1575. And historically, these temperatures are decided based on the metallurgical limitations, actually. The good news is that a lot of development has taken place in the metallurgical industry, and we have lots of exotic alloys. 40 years ago, it used to be HK40, then we get HP modified, but now we have microalloys. So basically, if we can withstand higher temperature, we can go for higher outlet temperature. So it's basically thanks to the metallurgical engineers and developing metallurgical alloys, we are, So one of the important parameter is radiant heat flux. And if you have a lower heat flux, you will get extra catalyst volume, lower tube wall temperature, and lower tube wall thickness. All good things are happening, but the furnace becomes expensive. Nothing comes free. If you got higher heat flux, you reduce the number of tubes, you increase the tube metal temperature, your tube wall thickness also goes up, and the flue gas temperature is higher. So the furnace size becomes smaller, but then you pay price in terms of higher tube metal temperature and higher tube wall thickness. The typical values in the industry are 20 to 26,000 BTUs. Lower number is always better, in my view. Higher number always produces problems. Some people even go up to 30,000, not me actually, but that's typically, yeah. So let's talk about the tube design parameters. We talked about tube length. So typical tube length is around 30 to 40 feet. And it's basically decided by the pressure drop, thermal expansion, and compression load. If you got a too long tube, then catalyst at the bottom will get crushed. So we have that compression load. So we don't want too long a tube. We don't want very high pressure drop. Also the tube diameter, if you increase the tube diameter, you're increasing hoop stress. You're also lowering the velocity, lowering the heat transfer coefficient. It will give you higher metal temperature and higher catalyst volume. So higher catalyst volume is good, actually, don't get me wrong, but basically everything else is not good. So typically the tubes are 3 to 5 inch ID, and the wall thickness is typically in the range of 11 to 18 millimeters or 0.3 to 0.5 or 0.6 inch. So as I said, there has been a tremendous amount of development which has taken place. Uh, Historically, we started with 2520, then we went to 2424, IN 519, HP modified has been used, and now we are able to use microalloys with titanium and zirconium. So these are rare metals. And what it does is basically we are able to get higher stress values leading to lower tube thickness. And we are using this improvement in metallurgy to revamp reformers. Like if you have a HK40 tube, you go to HV modified or microalloy. Now you can keep the same OD, but you can use the lower thickness. And with that, you can put more catalyst. So you can increase the capacity of your reformer by going uh, with lower thickness and improving. So the catalyst tube has a very important function actually. We basically hold the catalyst and gases under high pressure, efficient heat transfer, you know, and the typical tube metal temperature is generally outlet temperature plus 110 degrees. That's typically the operating tube metal temperature. Typical design margin is about 30 degrees on this temperature what we take. Steam to carbon ratio, high steam to carbon ratio favors products in reforming. If you see 1 and 3, basically we get much more this thing. Lowers the amount of unreacted methane or methane slip. But the most important thing is occurrence prevention of carbon forming site reactions. That's the most important thing why we use uh, higher steam to carbon ratio. So you can see the effect of steam to carbon ratio. This has been done by an engineer, Samantha Moore, and she has simulated 5 cases. She simulated a lot of cases, but I basically picked up 5 using steam to carbon ratio of 1 to all the way to 5. And basically that shows how much methane slippage is over the time. This is the steam gas or the steam what we are using. This is the heat duty of the reformer furnace. As we keep on increasing, the heat duty keeps on this thing. And then basically slip to duty. So basically how much slip to duty in ratio of pounds per million BTU. And then we plotted, and you can see after 3, there is no significant benefit. And that's why the steam to carbon ratio is generally limited to 3. After 3, basically there is no benefit in terms of operation. I mean, from 1 to 2 to 3, you can see significant benefit in methane slippage. But after that, there is no benefit, on the steam to carbon ratio. So that's why we use 3 or something. So these are some of the benefits on steam. Basically so 3 is a very typical ratio, and control is very, very important in terms of operation to keeping it. All right, we have a quiz time. So let's get back to you. What are the conditions which are favoring hydrogen production? Is it low temperature, low pressure, high temperature, high pressure, or high temperature, low pressure, or low temperature, high pressure? High temperature, low pressure. Thank you all. You got it all correct. Most of you got it correct. So let's move on. Thank you. So reforming reaction is favored by low pressure because the volume of the gases which are being produced increases. So lower pressure is better, but because of the processes which we are using, like ammonia loop or methanol loop, the industry still prefers high pressure reforming because they feel the compression cost of natural gas is much lower as the compression cost of the syngas, which is much higher in volume. So that kind of makes a difference, So you can see as the pressure goes down, the methane conversion uh, goes up. You can see over here. Similarly, temperature actually. So as the temperature goes up, the methane conversion goes down, or methane conversion goes up, so slippage goes down. So higher pressure is good for us. Higher temperature is good for us. And these are the effects of temperature, pressure, and steam to carbon ratio. You can see by going from 1400 to 1600 to 1500, lower temperature, we get less hydrogen. But if you lower the pressure, we get more hydrogen. So that's basically, have you already talked about high temperature, low pressure, and high steam to carbon ratio helps. This is the composition of the products with using different feedstocks. Refinery of gas already has hydrogen, so we get almost 80%. Methane and naphtha, butane. So basically different compositions. And you can see as the catalyst ages, the hydrogen concentration starts going down. Actually, methane concentration starts going up. So this is basically the effect of the catalyst activity. So let's talk about the steam methane reformer furnace. I think we have covered the initial chemistry, the catalyst, and let's talk about the different type of furnaces. And here I have got 4 furnaces for you: floor fired, down fired, terrace wall fired, and side wall fired. So the common thing over here is the catalyst tube configuration does not change in any of the designs. Whether you're looking at the floor fired or down fired, the number of catalyst tubes, the size, all those type of things are the same. What is changing is the firing pattern. In this one, we are using floor fired. This one is down fired. This one is terrace wall fired, or this is side wall fired. So basically, it's the fire side which is changing in all these designs. The catalyst tube, the catalyst configuration, the catalyst length, tube wall, everything remains the same. There is not much difference. So one of the most common design is down-fired reformer. And down-fired reformer is tubes are in a row, several tubes, and the burners are firing down from the roof. And because we can have one row of burners, one row of tubes, one row of burners, one row of tubes, the whole firebox is very, very compact. You can see over here, we need very few burners. And one of the things what they talk about is that the flames are the flue gas and the feed are going in the same direction. So we get maximum heat transfer in the bottom. So we have a very uniform tube metal temperature profile. However, in my experience, most of the problems occur in down-fired reformers, and we will talk in more detail in the future webinars. But you get what you pay for, actually. So if you are saving on the initial cost, you end up paying more. So there are several disadvantages: high heat flux, high TMT. You cannot do you cannot adjust the heat flux in these reformers. Also, the burners are located on the top, and the cold flue gases come out from the bottom. So most of these down-fired reformers are natural draft. One thing I can tell you is if you have any down fired, even though you're firing down, but because of the high temperature, flames have a tendency to go up. So no matter what you do, the flames will tend to go up. And when you have that, you will always end up with flame impingement in these reformers, unless they are designed very, very nicely. So most of the reformers, they suffer from flame impingement problems, high tube metal temperature problems, because that's just the nature. I mean, you're trying to have the flame straight, but it is not possible to have the flame straight because you're firing down. So anytime you fire down, you will see they are trying to go up. Side fired reformers have been there for ages now. I mean, in fact, most of the reformers in methanol and ammonia plants were side fired. They were pioneered by Halder Topsoe. Uh, they work on natural draft. That's another difference between the down fired and as you can see, there are basically lots and lots of burners on both sides. And generally, we have 6 rows of burners, and these burners are spaced at about 4 to 5 feet. That's generally how these burners designs operate. You can see there are burners in the center. So the difference in these things is there is only 1 row per box. That's a major difference. And because of that, the cost of side-fired reformer is always higher. But you can see this can be natural draft. The convection is located on the top and the stack can be located on the top. So there are advantages and disadvantages of each type of design. Terrace wall is another design which was pioneered by Foster Wheeler, and it basically has terraces. Each terrace is about 10 to 12 feet. So we can have 2 terraces or we can have 3 terraces. Most of the reformers have 2 or 3 terraces, and that's where the burners are installed over here. And there you can see over here, and the burners are firing along the refractory. Another difference I want to tell you, the difference between down fired and side fired is, or the terrace wall is, here it's a refractory which is radiating to the tubes. Whereas in down fired, it is the flue gases which are radiating to the tubes. Although the basic, I mean, if you go theoretically, it's still the same, but the refractory surface is much higher. AR, the refractory surface is much higher. So that's another major difference. And these things can be natural draft. They can have convection section on the top. So there are some advantages of terrace wall reformer. We can have the convection here, and then we have the stack on the top. I mean, the largest reformer I told you in the world, which I worked on several years ago for methanol, had 1800 tubes, was a terrace wall design. So you can make these. Another thing which is dictating the design is the modularization, which heater can be modularized better actually. Bottom fired reformers are not very common. They are mostly used for small capacities. Although the firing is very good actually. I mean, the only disadvantage is the hot flue gases are in touch with the hot tubes. So it's basically counter current, so it becomes kind of limitation. But for small capacities, you can always have a bottom fired reformer, not a problem actually as such. And then the convection section, actually we will talk more about convection section in other this thing. So it is very large and has a lot of services for recovering the maximum amount of heat from the flue gases, generally steam generation. So furnace draft, furnaces could be bottom induced draft or natural draft. And there are some furnaces who could be even balanced draft, down fired reformers. You can have air preheat, and then you have the forced draft firing and the induced draft. So we can have both types of furnaces, natural draft or balanced draft. Well, thank you very much for giving me a patient hearing. Now, I want to ask you a little bit how we did. Did this webinar match your goals, or how was it good, or we still need some improvement? Please give us your feedback. Almost everybody said good. Thank you very much. I'm going on a 2-week trip, so this feedback will be really, really helpful. So thank you all. Was the course content clear and easy to understand? I mean, my team has worked very, very hard for the last 4 weeks. So we need your feedback and we want to improve it, you know. So again, thank you very much. We will still continue to improve as our name suggests. Furnace improvements, we always keep on improving our stuff, you know. And then finally, a test for myself. So I'm not a very good speaker, actually, although I try. So well, thank you all. Thank you for your wonderful feedback, and hope you learned something new. And we please keep us in mind. Furnace improvements can help you improve the reliability of your furnaces. Uh, we can improve the capacity. We can reduce the emissions. We can improve the run length. So we have been there for 25 years now. We are not a new kid on the block. So give us a chance. We can definitely improve the performance of your heaters, reformers, cracking heaters, anything you talk about. We have a wonderful team. We can do CFD modeling. If you have any need for burner flame impingement, high temperatures, anything like that, please give us a chance. Please talk to our people in India or in Pune. Amarveer Chilka is our business manager for India. He can help you. He is a very nice guy. Uh, so again, thank you very much. It was really a pleasure doing this webinar, although it takes a lot of effort. So hopefully we will continue. Thanks and goodbye.